chemical reactions occur when chemical bonds are made and broken. Those chemical bonds are going to be those bonds that involve the valence electrons. To represent chemical reactions, we will have something like you see here, where we will have a reactant, which is the substance that we start with, and then throughout the reaction that is going to get converted into the products or the end result. So reactants and products is the way that we refer to what we start with versus what we end with, and we always have to pay attention to the arrow because the arrow is going to point to what we get in the very end. So it will always point to the products. The reactions that we have are going to be divided into three main types. The first type will be a synthesis reaction. Synthesis reactions are going to build or make things. So we're forming larger, more complex molecules from smaller pieces. Notice in the representation here, we've got two smaller pieces, and then we're going to combine them into something larger, more complex. The next type of reaction is just the opposite, because the next one, the decomposition reaction, we are taking things apart. So we're going to be breaking bonds here, and those bonds will be in the larger molecule, and then we take it and we break it into bits and pieces, simpler pieces, which is what you see represented. Now the third reaction is going to be more complex because this is going to reassemble stuff. It's an exchange reaction. There is some breaking of bonds, but then there's also some reforming of bonds too. So we're going to take some initial reactants or initial components, break them apart, and then take the pieces and rearrange them in a new way, and that will be what we get on the product side of it. Now, if we look at some examples of these reactions, so some specific examples of these reactions, here we have two of them. If we look at the first one is called a dehydration synthesis. So synthesis means that it is making something more complex in the end. And in this specific example, you can see we've got two small molecules. They're being combined into the larger molecule, and we do have some water being produced on the product side. So again, product is what we get in the end. It's because that water is coming out as a product that we use the term dehydration synthesis for this particular one. If we look at the hydrolysis reaction, which is the second one here, that is a type of decomposition reaction. So I'll just add that here, that this is decomposition, and decomposition was the breaking reaction. So we're going to take something that's larger. We are actually going to use some water as a reactant as well, and then we're going to break it into bits and pieces so we have smaller molecules on the product side. Now we also have some energy involved in this, so we see energy mentioned with both of these reactions, but one of them is using energy as a reactant and one of them is producing energy as a product. So some terms that refer to this energy usage are endothermic and exothermic. If we look at the prefixes and we know a little bit about what those prefixes mean, we can get an idea of what is happening during these reactions. Endo means in. So what we're seeing with that one is that energy is going in, which means energy is being consumed or used as a reactant. Well, that's really what happened with the dehydration synthesis, because energy, notice that there's no arrowhead on this side, so energy is actually going into that particular reaction. So it is a reactant, a necessary requirement if we were going to perform that reaction. And then the exothermic, exo means out, or just think of exit. Exit's when you leave. And so with this one, we're saying energy out. And I'll just write the energy on this side. So energy out means energy is going to be a product of that. And if you look at the arrowhead right here, it is pointing to the energy, and we said anything that the arrowhead is pointing to is a product. So the hydrolysis reaction is an example of an exothermic reaction. So if you have an exothermic reaction, it produces some energy, and then we can take that energy and use it to run something that requires energy. So exothermic reactions would provide the energy that an endothermic reaction actually needs in order to progress. Now, if we shift gears a little bit and we talk about water. Water is the most abundant substance that we have in organisms, and this applies to what we have inside of a cell. So in microbe, this would apply to that. It applies to the human body. It applies to plants. It is very abundant there. And there are a lot of unique properties, special properties of water that enable us to have so much water inside of our cells. So what makes water so special? Why are we going to have so much water inside of living organisms? Or why are we going to have so much water on the Earth's surface? Because that is another place where we have this extreme abundance of water. So first off, one thing that makes water special is that water molecules are cohesive. And cohesive means they stick together. Here's a picture of that. I'm sure you've seen this before, where you have droplets of water. Well, the reason why water forms droplets is because those individual water molecules are all sticking together. That's the cohesive nature of water, and that forms this droplet rather than us just seeing this splat on the surface. It's always going to have this little raised surface to it because they're sticking. Another important property of water is its excellent ability to act as a solvent, which really just means that water is really good at dissolving stuff. We probably know that from personal experience. We've dissolved things in water before, but it's not just in the kitchen or in the laboratory that we're talking about it being so good at dissolving things, because the majority of our cells, the majority of our bodies are water. So in those environments as well, water is going to have a lot of stuff dissolved within it. Another one is that water remains liquid over a wide temperature range. If we get extremely cold, it does freeze, and if we get extremely hot, it does turn into a gas, but there's this wide range of temperatures in the middle where water is going to be liquid. Water is also able to absorb large amounts of heat without changing its own temperature. So this is going to mean that if you're talking about, say, a lake, that lake tends to maintain a pretty steady temperature. It takes a long time during the summer for it or spring to actually warm up and heat up, but it's probably still not going to get as hot as the air temperature. And we could talk about the same thing with the cold weather. The water is probably going to be warmer than the air, because the air, even being cold, it's going to warm it up, or it's going to cool it down, but it's going to take it a long time to really be able to cool down that water. So it maintains a pretty steady temperature. And then lastly, water molecules participate in a lot of chemical reactions. And we just saw an example of that with the dehydration synthesis and the hydrolysis reactions. Another important concept to understand with chemistry is acids and bases. So if we just talk about what the difference is between an acid and between a base, we have an example of the two represented here on this slide. And the acids, first of all, these are going to be substances that dissociate or come apart, in other words, into one or more hydrogen ions. So we're focusing on the hydrogen ions here. Notice that when you added that to that beaker, then we have a hydrogen that came off. That's what an acid does. A base, on the other hand, is going to be a substance that binds one or more hydrogen ions. So the way that this would happen would be that you have something that has a negative charge to it, the hydroxyl ion there, the OH minus, we can see that, and that is going to bind up, kind of gather those hydrogens that are in the solution. So that's the acids and bases. We have a pH scale that helps to really describe what the situation is with the hydrogen and OH minus concentrations in solutions. And metabolism requires a very careful balance of the acids and the bases, or in other words, a very careful balance of the hydrogen ions, the H pluses, and the OH minus. So here we have the pH scale. The pH scale, really, it's just a numerical representation of how many of what is there. Notice that if we get to really low numbers, so like a pH 1, 2, 3, etc., we see here that the arrow is going up, and that is for that hydrogen ion concentration. I know it's pretty small in this particular diagram here. So a pH of 1 has a really high hydrogen ion concentration, whereas something on the other end of the scale, say a pH of 12, is going to have many fewer hydrogen ions. At the same time, as we go down and we get lower and lower, the OHs are going up. So OH is high on the bottom, so I'll just put that here. OH is high on the higher numbers. And so with the higher numbers, we're talking about anything greater than 7, because 7 is going to be neutral, and that's where our pure water falls. And then we're going to have high hydrogen on the low numbers. And that would be anything that is less than 7. So that's what the numbers actually mean to us as far as the hydrogen and OH, which we call hydroxyl ion concentrations. Now, organisms typically tolerate just a very narrow range of pH values. So in other words, they have to be probably within a number or two of their ideal pH range or pH number. Microbes, a lot of them can alter the pH of their environment using acids and bases, and so they're a little unique. They can secrete chemicals that can alter that particular pH value that we have there.